section here is going to start talking about moving lines, whether we move them left or right, up and down, whether we might stretch something out or we might shrink it. All that stuff is going to be talked about today. And essentially what I'd like to do today is this. I'd like to kind of go ahead and talk about all these characteristics today, but at the end of this, if we don't get to it today, we'll probably do it first thing tomorrow. Kind of like to come up with some kind of a cheat sheet that we create to make this more understandable and a lot easier as we progress through the rest of the year. So, 3.6 is entitled Transformations of Lines. Mathematically, prior to getting to this class, what do you guys know about transformations? Ever heard of the word? Say that again, Tori. So it's on a graph, so we're going to do something graphically, I agree. Let me ask this. You guys are probably, there's some movies out about these things. They're called Transformers. Anybody know those movies, Transformers? Show of hands, how many have watched those? Why the name of the movie Transformers? Tell me why. So they change from one form to another? Oh. So there's some changing going on. Okay? So transformations of lines, I want you to think of the same thing. We're going to take some lines and form something else. We're going to transform them into something else. Change them into something else. And essentially what we'd like to know, now this is going to sound like a bunch of Greek, and that's okay. We'll work our way through it. And we're going to simplify this as much as we can in the end. But our question is, how does the graph of a linear function f of x equal to x compare with the graphs of, watch this, g of x equal a times f of bx plus c plus d. This looks difficult right here, right? Oh, I think that I just put that in there, didn't I? What's the next statement right here, guys? This looks very confusing. Now, if you were down in the social studies department, we might say we want a friend. So decimals might be your biggest what? Ally. Ally meaning what? Friend. Is Russia our ally right now? I wouldn't say they are right now. Okay? Oh, little boy. You better take a social studies class and talk to them. A little bit of fighting going on between the U.S. and Russia about Syria right now. Right now. Right now. Yep. Yep. And the fact that Putin's just a mean person. Okay, goals real quickly. Let's get through these goals. How about a volunteer to read my first one for me, please? Volunteer to read my first one. Go, Emily.
Translate and reflect graphs and linear functions.
This word translate, how many of you have heard that before? Translate, okay. How about reflect? Okay. My day is ruined. Every day I wake up in the morning, I look in the mirror and see my what? My day is ruined right there, okay? But you know what a reflection is, all right? Sketch and shrink graphs of linear functions. We're also going to combine those transformations or changes of graphs and linear functions. And I'm going to show you how to do all that. But before we can even progress through this, we've got a ton of vocab that we need to make sure that we can use and communicate with each other before we start. So, I'm going to be putting some examples in this blank box. You don't want to be doing the same thing on your notes. But the first one says this, family of functions. Family of functions simply states that it's a graph of functions with similar characteristics. Graph of functions with similar characteristics. Most of our graphs that we've looked at in this chapter have all been what kind of a graph? Linear, exactly, linear. So basically, guys, anything that's a line, they may not be the same line, but they're going to have the same characteristic because they're linear. So in this chapter right here, we want to say that a family of functions would be anything that we've looked at that is, whoops, I didn't want to be there. Family of functions is going to be anything that is what we call, gosh, come on, linear. Okay, so jot that down in there. Everything that we look at as a family of functions today is going to be considered linear. Any lines you have, you're going to have it there. Now, you're going to hear this thing called a parent function. All right? Parent function. And a parent function basically is the most basic function in a family of functions. The one that we're going to talk about most is this. F of x in function notation equals x. Let me just show you right here, guys, what this means. Yeah. No worries. I have extras. Thank you. No, no worries. I've got a lot. You want a green one or a white one? Okay. Get rid of these ones. Get rid of these. Get rid of these. Are you happy now?
Yeah.
You won't lose those.
No way.
Yep. All right. So right here, guys, the parent function I talk about the most is this right here. Parent function for all lines is going to simply be f of x is equal to x. So all I'm going to punch in, you guys know what f of x we can replace with which variable? Y. So just punch this in. Y equals x. All right. Parent function because that's the simplest function I can put in. Also, notice which point does it pass through? 0. What point is this right here that I'm pointing at? 1, 1, isn't it? 2, 2. 3, 3. What's true about the x and y values here? 4, 4. 5, 5. What's true about the x and y values? They're all the same. Right up here, I just wrote in here the simplest line you come up with is y is equal to x, where y is equal to x. Okay? All right. So that's going to be the parent function we talk about most. Now, we're going to start doing stuff with this line to form other lines, and we're going to talk about the characteristics. Hey, did we slide that line up to get that? Hey, did we stretch something vertically? Did we shrink something horizontally? Those types of things. And in fact, that is the type of stuff I'm looking at right in here. Transformation right here was the next one. It says a change in the what? Size, shape, position, or orientation is always an interesting one. Who wants to be my twin right now? KB, come here. I love orientation. We all know what it means to change a size, right? We all know what it means to change shape. We all know what it means to change, hopefully, position, move around. But the one that's confusing is orientation. Now, when I wake up in the morning, I'm looking into the mirror. There's my mirror image right there. Okay? Or maybe she's looking in the mirror and this is her mirror image. Do you feel good about yourself or not so good, you know? Oh, geez, come on, humor me. Okay, hey, here's the deal. Which hand did I raise? I raised my right, but it's going to appear what? That she raises her what? Left hand. So basically, orientation means everything is kind of the opposite. If I raise my left hand, she's raising her right, the opposite, right? If I stand on my right leg, she's standing on her left leg. If I do this and this, all right, good enough. You get the point, all right? You get the point. Thanks, KB. Basically, it's just going to be some kind of a movement. Transformation means some kind of a movement or a change. Kind of like the transformers that we talked about. All right. Volunteer to read translation for me. What's translation say? Go ahead, KB. Okay, so basically what it would mean is this. You would take some kind of a shift. You would either move it left and right, up or down, or a combination of those. So is the size ever going to change? Size ever going to change? Be like this. Here's a graph. Here's a graph for you. There's my line. Okay, I'm going to move it right. Size change?
No.
Still the same, isn't it? Translation just means slide it somewhere. Okay, translation, I'm going to put that word up there for that. Simply put, the word translation just means to slide it somewhere. Okay? Slide somewhere. Okay, reflection. You get the idea what reflection was when we compared that with Kelly and myself? Reflection basically is take something and flip it over a line. Okay? So the word that I like here is this. The word I like is flip. Reflections are simply flips over some kind of line of symmetry. Well, we'll talk about that here in a bit. Okay, the ones that I think are going to be difficult are the last four. The ones that I think that will be difficult are going to be the last four. Guys, horizontal shrink is going to be a transformation that takes place by multiplying the inputs x by a value of a when a is greater than 1. This is where things get tough. All right, we might have an original function f of x. I'm going to write this down over here. Original function might be a function f of x. I don't know what it's equal to. But they're saying a transformation that takes place by multiplying the inputs. Which variable, guys? Well, the inputs are my x variables by a value of a when f of a is greater than 1. They might say graph the original function. And then they're going to come back and say, hey, if something shrinks horizontally, and I'll show you what that means here in a second, this might be graphing something like f of, in parentheses, maybe 3x. Okay, f of 3x. They're saying my a value for some kind of a horizontal shrink has to be greater than what? 1. What do you think the a value is in the example I've provided over there? 3. Okay, so just keep that in mind. Then they talk about horizontal stretch. Instead of something shrinking horizontally, something that would widen out like this horizontally would be considered horizontal stretch. And that is a transformation that takes place by multiplying the inputs x by a value between what and what, guys? 0 and 1. So like a fraction, part of a whole, if you will. Part of a whole. So I might say something to the effect of graph f of, how about a fraction between 0 and 1, gang? 1/3 x. Okay. Let's go 1/2. 1/2 x. Perfect. Okay. And again, I think that when we get to the examples and decimals here, I think that this will start to make a lot more sense. Again, just as I have horizontal shrink and vertical shrink, we also have, just as we have horizontal shrink and horizontal stretch, we also have a vertical shrink and a vertical stretch. And quickly, just to show you what's going on here, vertical shrink is going to be any transformation that takes place by multiplying the outputs by a value between what and what again? So again, if the original, and again, I should have written this up top, if the original is f of x, an example of what a vertical shrink would look like would be the following. They might say graph, maybe, I don't know, 2/3. Is 2/3 a fraction between 0 and 1, gang? 2/3 times f of x. This time that a value is no longer inside of parentheses with the inputs, but rather it's on the outside to help the outputs or change the outputs. Okay? And then finally into a vertical stretch. The same exact thing, but instead of a being between 0 and 1, it says a has to be greater than what? 74. You want to use 74? So you might say graph 74 times the original function. Okay? So the way I think about it is this. They're going to talk an awful lot about are the inputs affected or are the outputs affected. Okay? Guys, these a values that I've thrown in here, are they inside of parentheses or outside of parentheses? They're inside of parentheses. What do they affect? Inputs. Stuff inside that affects the inputs. These coefficient values out in front of f of x, are they inside parentheses or outside parentheses? Are these coefficients inside these parentheses or outside of them? Outside of them, right, Nolan? So that's going to affect my outputs. So that's one way we'll remember this, okay? Now, there's a ton of stuff there that I've talked about that you might be looking at me like, Carson, you're up here and I'm not even close, okay? Let's look at some examples and tie this stuff together, all right? First things first, have you got down what you need to have down here? Is that a yes? All right. Everybody's a yes? Give me some sort of science. You're alive right now. All good? All right. Well, let's take a look here and let's start rolling with this. Decimals is going to be important. In fact, I'm going to hand out some rulers today too. So when I hand this out, grab a ruler. And the rest should be coming around here quickly, all right? And when we get done at the end of class. Just throw them back in there, guys. I think we're gonna have enough time to get through the first 2, 3 examples. We're not gonna finish this today, and that's all right. Thanks, kiddo. I'm sorry, I don't know how to count. And that teacher can't count. That's terrible. Thanks, Elisha. All right, just a disclaimer: the rulers are used to make straight edges. That's all you need them for. All right. All right. Hey, quickly, guys, let's get started on this. Example 1 is going to start talking about what a horizontal and a vertical translation look like. Now, I'm going to graph this, and again, we'll use decimals to confirm this stuff. A lot of the stuff that we'll do in the notes, yeah, we'll graph it out and talk about the characteristics of it. But when the assignment starts saying, hey, start graphing these and then talk about the characteristics, where do I want you to go for your graphing? Okay, decimals, exactly. All right, here's the example right here. Horizontal and vertical translations. Translations meaning a slide, either left or right or up and down. In this example, we're going to involve sliding up or down or left or right. So the first idea is here is saying, you know what, let's let this function f of x equal 2x plus 1. Okay? This is much like slope-intercept form. So remind me again how to graph this. Where would I start? Okay, so you're saying start at 1 on the y-axis. So I'm going to give me some room to work here. So right here. That's where you want to start, right there, right, Tori? How about my slope to that point according to the function that you have in front of you on paper? 2. So from here, rise 2, run 1. All right, I'm going to kind of, well, I'll go ahead and get this graph now. So with your straight edge, go ahead and graph your line. Tell me if you agree with what I have and what you have here. You guys agree with that? Everybody agree with that? Again, y-intercept is 1, and then the slope is 2 for this original function, isn't it? Everybody agree? Okay. So here's what I want to talk about, guys. Here's what I want to talk about after we've got that done. Our original function right up there is f of x. F of x is the original function. And the point I want to make about this is the following. It says, well, f of x right here is really equal to what function thing? What was f of x equal to? Okay, now, they want you to go ahead and graph the following. They want you to graph g of x such that it's equal to f of x minus 3, and then they want you to talk about this transformation and talk about what's happening here. Guys, this is the part I want you to understand, and this is the part that can get confusing for kids as we progress through this stuff right here. But what function was given, guys? What function was given? F of x. We're going to write a new function, g of x, but it's going to use which function somehow? F of x right here, all right? And 2f of x we are subtracting how much? 3. In your description of how this translates, you need to talk about the original function and how it's related to that operation of minus 3, okay? If something moves 6 units one direction, can you say, oh, the minus 3 did that? Not necessarily. You have to say, well, it moved 3 directions this way, therefore, that's the effect of subtracting a value would have. So let's check this out. Here's what I would suggest we do. First of all, what they want you to graph, g of x equal to f of x minus 3. Kids, right here. Anything you can choose to substitute for f of x. Anything you choose to substitute for f of x. What was f of x equal to in the beginning? 2x plus 1. So where I have the f of x right here, I can replace that with 2x plus 1. So realistically, guys, g of x is equal to this function f of x, which is what? 2x plus 1. What is this replacing again? What's this replacing though? F of x. And then to that we are going to subtract how much? 3. Subtract a 3. Alright, this is really the same and the same. G of x, you know what? G of x is really the same as 2x. What's the plus 1 and minus 3 going to combine to? Minus 2. I've taken my f of x. I've substituted what the f of x equivalency was. I've simplified as much as I can. Our job would be to graph a new line. Once I've got this new line graph, we want to talk about the description of the transformation. What effect did negative 3 have on that original graph? So here we go. We're now looking at graphing this. So instead of an intercept being positive 1, what's it say the intercept is now? Be a negative 2. So where am I starting? Well, down here. Oh, geez, that's way off. Hang on a second. Calibrate, calibrate, calibrate. All right, let's try this again. What was the new y-intercept? Oh, I like that much better. Okay, what was the slope again? Rise 2, run 1. Okay, now before I even draw my line for this, my question might be the following. What? Just looking at the points I've graphed. Just look at the points I've graphed. Look at the points in the original f of x and the points in the new g of x. Is there any connection you can make using a value of 3 or negative 3 in this case? Is there any connection you can make about how this line right here would fit these points right here? Say it one more time, Tori. 3 below, okay? Oh, actually, it's about 60 degrees. Not 3 below. I'm kidding. Am I suggesting that you said, hey, here's a graph, or I guess maybe I should say it differently. Am I understanding that you're saying take the original graph and slide it down 3 units? Is that what you're saying? So here's this graph right here. So you say put it right there, something like that. Check it out, guys, from point to point. The 2 points that are here and here. First of all, we already had the lines in here, or the points in here, where the intercept was negative 2 and the slope was 2. Guys, if I take this point and slide it down 3 units, does it fall there? Does it fall there? If I take this point and slide it down 3 units, does it fall there? Why is 3 significant again this time? Somebody tell me why 3 is significant. Why is 3 significant, guys? What's in the problem? No. Help me out. There's a negative 3 in here. Why is that negative 3 significant? Well, you just said this moves down 3 units. That's exactly what Tori said. So describe the transformation. The minus 3 out here like this. Minus 3 means to move, or transform, if you will. Up or down? Up or down?
Down.
A quick question here. Was that minus 3? It was something that's happening inside of parentheses or outside of parentheses? Outside. Outside parentheses affects outputs. Outputs are a change in a y value. If outputs are a change in a y value, does moving down seem like a reasonable direction to go if it affects y values? It does, doesn't it? It does. Okay. All right. So what's the difference between this one and the next one? I'm going to do this next one with decimals. Check it out, guys. F of x equal to x minus 3. Got a minus 3 in there again. However, where's the minus 3 this time? On the inside. What do you think this is going to affect then? The inputs or the outputs, first of all? Inputs, which are x values. Do x work horizontally or do they work vertically? They work horizontally. So do you expect to slide left to right or do you expect to slide up and down? Left to right. Let's check it out. This is where decimals is going to save you a ton of time. We'll graph this here. But this is where it's going to save you a ton of time. Let's check this out. There's my original function. What was the original function? 2x minus what? Or was it 2x plus 1? All right, so what they're saying here is this. They want you to say, instead of putting an x in here, they want you to put in, what's the input they're using in parentheses? X minus 3. Well, no problem. Let's check this out. I'm going to type that in just as this. I'm going to, instead of putting x in here, I'm going to punch in x minus 3 as an input, and then plus the 1. Let's see. See this point right up here? See that point right there at 0, 1? And this point right here at 3, 1? Okay, so how far to the right did that move? 3 units. Okay. Now I want to show you the mathematics behind that, but can you get a visual off of this right here? Again, you have to use 3 somehow. Here's the original one in red. Looks like it went what direction? Looks like it went what direction? To go from red to blue, what direction? Right. Some people might argue and say, hey, I think that this just slid down. I think it slid down. Could I also say it slid down? Could I slide that red one down on top of the blue one? Could you slide this graph down to this? Good. Here's the deal, though. This point to this point, how much distance do I have? Well, 1, 2, 3, 4, 5, 6. Was there a 6 ever listed in the part that we had the graph when it said graph that? Was there a 6 ever listed? No. We've got to find some value of 3. In this case, 3 to the right is what you're looking for. So how does this work? Why does this work this way? Why does that graph appear that way? Well, here it is. They're suggesting right here the following. First of all, what was f of x equal to, guys? What was f of x equal to? Originally. At the top of that page. 2x plus 1. Okay? So what they're asking us to do here, guys, is to input. Instead of having just x right here, what are they asking you to input now? X minus what? 3. X minus 3. Okay, so what this t of x function would then become is the following. T of x is going to equal 2 times, let's input all of x minus 3 plus the 1 here. Okay, I want to simplify this, so help me distribute. Help me distribute. Where are you at here? 2x minus 6. All right, how about the negative 6 and the plus 1? So we've got 2x minus 5. So what I would really be graphing here is 2x minus 5. 2x minus 5. Well, no problem. No problem. Back to decimals right here. This is what I put in like that. When I graph this right here, the 2x minus 5, do I have a minus 5 as my y-intercept? That worked, didn't it? How about my slope of 2? Rise 2, run 1. Is that checking out? Is that checking out? It is, isn't it? Okay. So here's what I want to do first. Here's what I want to do first. Five minutes. Okay, do this for me. How much room do you guys have at the bottom of this page? A lot or a little? Check the notes out real quick. Yeah, I'm going to get you a different sheet here. I think I'm going to stop there right now. I'm going to stop for that part right now. We'll pick the rest of this up tomorrow. Don't forget, when is 3.5 due? Friday at 4, and that's the only thing you should be looking at. Also, that practice test that you guys have, be taking a look at that. Make sure my rulers get back into the container up here, and we'll pick this up tomorrow from here, so make sure you have your notes with you again.